All right, so welcome back. So now we have a talk that's applied to energy applications that some of us have worked quite a lot on. I guess you stick to wind?
No.
Ah, you don't stick to wind. Okay, cool. So in Plus we'll consider several applications, which would be good inspiration for the discussion afterwards. So that's perfect. So we have an hour plus minus now.
Great,
Thanks,
so much.
Jethro.
So for those of you who haven't met yet, I'm Jethro Browell from the University of Strathclyde. I'm going to speak quite generally about a range of applications. So if you want to know more detail, maybe ask a question, or we can talk about it later. It is mostly wind. I think I'm going to have 5 slides on solar, and I'm going to maybe talk about demand in a kind of motivation kind of context. But yeah, mostly examples from wind. So I'm going to show some kind of motivations why I'm interested in high dimensions. And actually, I think this topic breaks down into 2. One is where we have high dimensional forecasts. We're interested in making predictions about maybe a high dimensional quantity, maybe spatial or temporal or both. But we also have a high dimensional challenge where we have lots of input features. So it's kind of high dimension on the input side, even if we may be only interested in univariate output. So I think those 2 things are quite separate, and I think I'll touch on both. So after the kind of motivations, got this one example from a hierarchy where we have this very high dimensional input space, but we're only interested in forecasting the wind farm's output. So that's the first case. And then the other 2 are about temporal and then spatio-temporal dependency structures. And I want to talk about how these dependency structures themselves are actually dynamic, and how we can start thinking about modeling those dynamics with some examples. Okay, so I also need to acknowledge lots of collaborators. So in order that I'll present results, so Kieran and David, colleagues from Strathclyde, and then the solar work I did in the US, kindly hosted at NREL, and then some of David's colleagues actually from Reading provided me a lot of support on atmospheric regimes, which we were using to condition spatial temporal models. So big thanks to all of those people. So to give you a sense of maybe the scale of dimensionality I'm interested in, on the generation side, we have almost 1,000 wind farms in GB now, only maybe 150 or so with readily accessible metering, but it's a lot. And then on the solar side, we have 1,300, but almost none with readily accessible metering. Though some of them are voluntarily signed up to provide this. And this is a real challenge, especially for the network operator whose decisions are driven by the network, which is itself another spatial layer here. So if we have a big forecast error affecting one cluster of generation, that has a big impact on the network. And this is why I'm interested in spatial temporal forecasting. So whenever we make a forecast, we want to understand the uncertainty on that, the implications of any errors on system operation are what I'm interested in.
Wind is left, solar is right.
Yes, sorry. Yeah, we don't have any 2 gigawatt solar farms, but we do have a 350 megawatt solar farm in planning. So imagine how many fields.
Well, so when you see the locations, I think it makes sense.
Yeah, absolutely. And I think, not offshore. I think that these offshore wind farm clusters are, I think, a key feature of GB, and I think they're going to emerge elsewhere. You can imagine if, so a kind of classical error in a weather forecast is getting the timing of a weather front wrong, right? So you can imagine getting very different characteristics if this weather front is kind of parallel to the alignment of the installed capacity. That error is going to give us a large error when we look at our aggregate wind. But if the weather front was moving perpendicular along this capacity, we have a very different structure. And what things that might look very similar in the meteorological forecast have very different impacts on the energy system. So this is why we care. We have a similar picture on the demand side. So in GB, the transmission system connects the distribution networks at around 350 locations, each of which are metered, and each of which today are forecast individually by the system operator. But then below that, we have another 500,000 substations potentially, and then the 40 million smart meters if they're ever all installed. So the dimension is orders of magnitude bigger on the demand side. So I think the problems here that I'm not going to talk about anymore are quite interesting around how much coverage do we need to build up a good picture of what's happening in the whole, right? We don't need to have live data from all 40 million smart meters to understand what's happening on the demand side. So some really nice work to be done there, I think, on coverage. How much coverage do we really need to understand or answer the questions we're interested in? Cool. So they were spatial examples. On the temporal side, we know forecast errors often have strong temporal correlation structure, which we can't ignore, especially in some decision-making problems. So storage management is a classic one. You can't discharge once you're empty. You can't charge anymore once you full. Big temporal constraints. And the same for conventional generators with minimum, maximum uptimes, downtimes, and so on. You turn off, even if you turn off a wind farm in GB, it maybe has to stay off 4 hours. And you have to consider that when you make the decision to switch it off. So, in lots of these decision-making problems, we have these temporal constraints are really critical. Yeah. Okay. So finally, I think we have a whole talk on hierarchies tomorrow, right? So I'll maybe not speak too much about this. But hierarchies are everywhere, and this is a great advantage. It gives us lots of information, the opportunity to go to a lower level to have more detail and understand better, or take advantage of smoothing if we aggregate up. So this is really helpful, and I'm going to talk more about that in the next example. So let's move on quickly. So in a wind farm is made up of many wind turbines. So this is a really simple hierarchy, and we can leverage the data which is routinely collected from individual turbines to try and help us make a better forecast for what this wind farm is going to do. So that's what I'm going to talk about briefly now. So the name of the game, and some specific games like GEFCOM, is to make the most accurate forecast you can, given some explanatory information in the form of numerical weather prediction usually. And lots of the skill comes from this. It's essentially learning a power curve, so mapping the weather forecast to historic power output, and assuming that relationship will be the same in the future. So the challenge is getting that quite complicated relationship modeled well. So we can do this at the wind farm level in a classical supervised learning setup, where you have your target variable, the power, and then how many input features you have. And in the kind of more successful applications, you might engineer loads more features in the weather forecast as well. And then it's always, we had some nice pictures of overfitting earlier in the morning, right? The challenge is it is something we see in the historic data, a real feature, or are we overfitting if we try and model it? So our thinking with this work was, well, if we have the picture of what's happening at the individual turbine level, maybe we can better distinguish between true features of the data, true features of this relationship between the weather forecast and the power output, and just random variation. Okay. Yeah. So I'm interested in, can we just take advantage of having greater detail in the hierarchy? I don't really care in this application about coherency. I kind of explained all this already. Okay. Yeah, I think the key thing here is the top. So a wind farm power curve is quite a messy thing. It's affected a lot by the layout of the array, by the terrain, by vegetation, all the rest of it. So it can be quite messy. So here are two wind farms we're going to talk about. One you can see is nice and regular, almost perfect grid. And actually the terrain here, you can't really see in the picture, but it's relatively simple. The second one is much more complicated. You see the layout is more complicated, and actually there are 3 hills here. So this cluster is a hill, this cluster is a hill, this is a hill, and also on this picture is a West Coast main line. So if you ever got the train to Glasgow on the West Coast, you've been through this one. Okay. So now everything I'm going to talk about you're using the same statistical learning technique, so using gradient boosting machine for quantile regression because we want a density forecast for the wind farm's total output. The question is, how can we make use of knowing what individual turbines have done historically? And can we make a better model, make this F even better by adding extra features, perhaps derived from knowledge of the turbine level. So the first method is quite simple. So we produce a forecast for each individual turbine's production. So it's X1, 2, 3, 4 up to 35 or 56, depending on the wind farm. And then we give those individual forecasts to our gradient boosting machine. So we're kind of a very simple approach. It's almost like a forecast aggregation. We tried the classical impose the structure of the hierarchy and just add them up, and it was very, very bad. But maybe we can just give these features directly and help.
Those at the bottom level are quantile forecast already or not?
No, these are just deterministic in this case. Yeah, and maybe some other features. So we give the deterministic forecast to the individual wind farm, but then we can also create features like the standard deviation across the wind farm, the min, the max, and not pass all these on.
We can say deterministic forecast in the expected value.
Yes.
And so you are predicting the quantiles according to the forecast of the expected value.
It's a bit what
Yeah.
you were showing
Yeah,
there.
yeah, exactly. So this is method one. It's okay. But because we're interested in the density, there's an alternative approach, which would be to try and estimate the whole joint distribution for the power output for all the turbines in the wind farm. So that's what we do in the second case. So now we do forecast all the quantiles for each individual turbine. So we have a density forecast for each turbine, then model the spatial covariance structure using a Gaussian copula, and then we have the full multivariate distribution for the power output from every wind turbine, and it's then very simple to produce the density for the sum of all the dimensions, right? So this is maybe a bit more complex, but it's also nicer because we have all the full information. So I think the next slide is a picture of some of these covariance structures. Now we have the additional challenge of estimating the spatial dependency matrix, which is a nice high-dimensional problem for us. Okay, so I have these two methods. But maybe the thing to point out, however, is that when issuing a forecast, end-to-end, the only input is the weather forecast, and the only output is the density. It's just a slightly different description of what's in between. So for a nice regular wind farm, we have a nice regular covariance structure. And this is just a very simple parametric covariance matrix where the covariance between two wind turbines is a function of its distance, like an exponentially decreasing function of the distance. So you can, if you pick out a wind turbine and then find it, here you'll see its neighboring turbines have a very high covariance. Ones further away have lower. And actually, the covariance is very strong between all wind turbines, so I don't think it's below 0.6 anywhere. Right? So very high correlation.
Can I ask you something, Jethro? I mean, did you say check that out first before to decide you get this exponential?
Yeah, so we also compare the empirical covariance matrix as well, and then we estimate the parameter of the exponential decay using maximum likelihood. Quite nice. I don't have a picture. I've got a picture for the same thing for solar in a few slides. And then we have the same thing for the second wind farm, but now the structure is much more complicated, and we have instances of much weaker correlation as well. And this was quite nice. But we found both approaches were very effective in improving our prediction. So this taking a more detailed picture of what the relationship was between the weather forecast and the output from the whole wind farm gave us overall improvement. So for the simple, well, in both cases, both with the turbine level features, sorry, I've got a pointer. How do I point? There we go. This is just with the turbine level features. This is with the spatial copula. So both improve against just the GBM with no features, and we also implemented a nice analog ensemble for benchmark as well. But so in both cases, this more complicated picture, even though it's a bit more effort, gave us some really nice improvement in both the skill of the P50 as a deterministic forecast and also the CRPS for the whole next. This was a really nice case where we deliberately went to a higher dimension, not because we had to, but because we saw potential advantage in it, and it gave us some nice improvement overall. So I guess the question is it worth the effort? I'll leave that to you guys. But there is a huge amount of data being collected by all utilities now, from the SCADA systems that we heard more about on Monday, and I suppose there is value in some of it if you can take the time to leverage it. Right. Okay.
Sorry, can you describe a bit more this GBM and GBM plus T? What's fundamentally the difference, you said?
So GBM is the only features that's given are derived from the numerical weather prediction. So it's wind speed at different heights, this kind of thing, only.
As like one average for the whole wind farm? Or?
Yeah. So supervised learning GBM targeting the wind farm's output. GBMT has extra features, which are the deterministic forecasts for the individual turbines. And
Yeah.
other features to us.
Can I just briefly ask, what about the wind direction? Did you take that into account in the forecast?
Yeah, so that's there too. That's there too.
Right, okay. And because that would affect the dependence between the...
Yeah, absolutely. And I think that's where some of the challenges come. If you wanted to draw a picture of a wind farm directional power curve, you would see all these features to do with when the more turbines are in the wakes of the others relative to the other direction, or when the wind is, you're getting more of a speed up effect over the hill and this kind of thing. And actually estimating that surface is a really difficult thing to do. And of course, all the data is noisy as well, so you don't know if what you're seeing in the data is, because when the wind direction is some specific vector, you are actually seeing different behavior, or if it's just random variation. And I think what we think is happening here is we're better distinguishing between this true relationship and the random variation, which is why we improve it. Okay. So that's one. So the next is now, I guess this was a kind of spatial example.
I have another question.
Sure.
When you do the return boosting with all this deterministic feature, what you call the deterministic forecast, there is only a time series feature when you return boosting. There is no variables and doesn't depend on time. Like you could have included the position of a wind farm, for example, or data information about the wind farm. To have maybe to have a chance to build some clusters of wind farm, for example, some groups of wind farms.
So it's just one wind farm.
Not wind farm, wind turbines.
So you mean more explicitly take into account the kind of physical
Or global feature of wind turbines, like its positions. Do you think it will be interesting to do that?
Well, the position never changes, right? So we're interested in learning the relationship between the weather forecast and the power production.
Yeah, but maybe because you put all these wind turbines feature into a single gradient boosting, this gradient boosting could build automatically some clusters.
So you need another intermediate step where we...
Yeah, but you could include it into the model also.
Yeah.
Extra
features. Yeah, for sure.
It's just a question, maybe.
No, I mean, like I said, so we included a few, like the spatial standard deviation for the forecasts and the min and the max and this kind of thing. But not,
I don't know if it's relevant to us.
Yeah. Well, if it doesn't change, I don't see how it adds value. So metadata like the position would never change, so I don't see where it adds value. Don't know. Maybe if you provided some information about the the ordering, so you knew where the front row was and that kind of thing, potentially. Yeah, it's an interesting idea.
Yeah, I don't know a lot about it, but the wind turbines, some of them may be out of operation for maintenance or something
Right.
like that. So you have this information as well?
Yeah, and actually that's a big advantage of the second method, because we're producing the multivariate distribution for all the turbines. If one's off, that's very easy to deal with. Whereas in the first method, you're missing a feature, and what do you do? Do you refit the whole model where you don't need that feature, or yeah, it's an issue. So.
But you just put this as features, 0, 1s,
So in the second
not
case,
at all, it's just 0.
yeah, well, we assume we know if the turbine's down for maintenance, right? Because we're pretending we're the operator.
So then, some kind of manually, you put that forecast to 0.
Yeah. Okay. So the next example of high dimension is a temporal one. So in solar power forecasting, in producing scenario forecasts in general, we want to have a really accurate representation of the temporal structure of the future values. The challenge in solar power forecasting is the behavior of the solar production. It can look very different on different days. So it's a very clear day, you have very stable output, and it's very nice. And if you have any forecast errors, then they tend to be caused by something which persists for a very long time. So your forecast might be a little too high or a little too low, but it'll probably stay that way for most of the day because you've got something wrong, like aerosol content, and it's that error is going to persist for a long time. Whereas on maybe a partially cloudy day where you have lots of broken clouds, forecast errors are going to be much more random as a cloud passes over that maybe you weren't expecting. They're very difficult for weather models to forecast and so on. So we would see much kind of noisier error structure because the underlying processes doesn't have the same inertia as the clear day example. And we want our scenario forecasts when we make them to reflect this. It's going to be really important, for example, if you have a combined solar and storage facility, right? If you want to smooth out noisy errors coming from clouds, that's one thing. If you want to shave the peak, that's another. Okay. Yeah, so here's a nice picture of a clear day and a partially cloudy day, for example, where it's very different. And then we have similar on overcast days where, again, the forecast error will persist for a long time, but it has a different underlying cause, so maybe it also has a different structure. So if we've got the thickness of the cloud wrong, it's probably going to be wrong all day. These kind of things. So we have different drivers of forecast errors, giving us different temporal structure. We would need to model this. So here's the plot here I wanted to see earlier for the wind, but in the solar example. So this is temporal covariance matrix now. So we're talking about forecasting from 0 to 48 hours ahead. And this is our error structure, again, the matrix of a Gaussian copula. So I won't give you the details of how we produce the marginals, but it's the covariance matrix of the Gaussian copula. And the circles here are the empirical covariance, and then it's really nice to smooth out some of these noisy estimates with a parametric estimate here. So in this case, we have the big peaks at 24 hours, right? So if we have some error, 5 o'clock today, we might also have a similar error at 5 o'clock tomorrow. I'm not sure to what extent that's a property of the weather forecast, or if it's some challenge to do with the envelope of solar power, right? It kind of imposes the structure, and if we're not dealing with that completely, if we're not completely removing that, then we'd expect to see these features with 24-hour multiples of that. So I can't say for sure which is contributing more here. Okay. But this is just for one type of day, right? So the question is, how different does it look on different types of day? So I should have labelled the clusters, but I think green here is the clear day, and then we have the cloudy day, and then red is the overcast. Is the partially cloudy, sorry. So we have much weaker temporal correlation. We can see the same thing in these covariance matrices, right? So on the clear day, we have a much thicker diagonal here, so our errors are persisting in the same direction for an extended period of time, especially compared to the partially cloudy day where we have this really narrow diagonal, so our errors are not persisting for a very long time. They tend to be positive, negative, much more random. But if we want to use this information in making a forecast, we also have to consider the cross terms, right? So what if we predict clear weather and it's actually partially cloudy and so on? So it becomes very messy, and somehow we have to turn this into an error covariance matrix for the forecast issue time we're interested in. So that's the next step. Is I haven't told you how I've defined clear, partially cloudy, and overcast, but it's derived from the numerical weather prediction. So when we get a new weather forecast, as well as all the variables we want to use to make our marginal density forecasts, we also have to assign a weather type to each lead time, and somehow reduce this covariance matrix so that it's the right dimension again, which we do here. And it's a really nasty problem. I'm not very happy with it, how to do this. And also we have all these periods where we have no information when it's done, right? So that just goes away. But I think forming these covariance matrices where you potentially have cross terms between cloudy, between multiple regimes is a real challenge. And if anyone has any nice ideas for how we can deal with this, then I'd be really keen to talk about it. And just to show that it works nicely, so here are some scenarios for that. They don't tell us anything, but we can look at some multivariate scores to see how we're doing. And so the identity here is just assuming no structure, so no temporal structure, just taking the covariance matrix to be an identity, kind of naive. And then the static covariance matrix is just one regime, so assuming that things never change. And then dynamic is switching based on the cloudy, clear, partially cloudy. And you see we're going in the right direction, but it's very, very early days.
Sorry, what is the score?
So we've got the multivariate energy score, which is known to not be very good at discriminating between covariance structures. But in all these examples, we have exactly the same marginals. So any difference we're seeing here is either sampling error or because of the covariance structure. So we're going in the right direction. And then the variogram score is a proper but not strictly proper scoring rule that looks mainly at the covariance structure. It's invariant to shifts in the mean. But there are no shifts in the mean here, right, because the marginals are exactly the same. Okay.
So I just had a question to the plot. I think you showed it once, but you see every day you see one scenario which peaks a lot, which looks unrealistic. Is it?
Yeah. So actually, in the data, we had quite a lot of those, and so
this is a measurement, right? Isn't it?
well, but there are some effects. So it's
Because you have an upper limit.
but it's a kind of a soft upper limit, and you have the occasion of maybe getting lensing, so where the clouds can form and give you a small boost, or you can have a reflection from clouds and not directly over the top, increasing the amount of diffuse radiation. So the clear sky index isn't a hard upper limit. And so yeah, so modeling that's a challenge as well.
What's the lead on the forecast? Is it bad or?
Yeah, 0 to 48 hours. So, yeah. So two solar days, but using the locations in the US, right? Which is why it's not. So this is maybe probably a noon issue time, but the solar peak is at like 6 p.m. or something because it's in Colorado. Okay.
What is the duration of your data set for training this kind of models?
This was 3 years, I think. Training on 2, testing on 1, but I should check. But that's the kind of typical duration.
Do you have maintenance activities and things like that going on in the farms?
Yeah, well, this data set is actually from not from solar power production, I should have said. It's from a measurement of solar radiation. So it's a maintained sensor as part of a national network, so it's quite high quality data that doesn't have those issues, but for sure. Actually, while I was visiting, there was a hailstorm that smashed a lot of solar panels. So that wasn't included in anyone's forecast, I don't think. Yeah, a lot of cow windscreens too. So be careful if you go to that.
Okay, can I ask you?
Yeah.
I was talking about the sensitivity. If you go completely crazy with your covariance structure, how bad does it get in the score?
What do you mean completely crazy?
I mean, here you fit a covariance model, and somehow you compare your covariance models.
Yeah.
Let's say that you want a base case. So I don't know if you have a naive predictor. I don't know.
So the identity here is assuming just a diagonal covariance matrix. Right.
So no covariance. Okay, so that's your
So
dumb.
Yeah.
dumb-
So that's
okay.
the naive. And so we get solid improvement going to the single never changing covariance matrix, and then about half again going to the dynamic one.
And you say the clustering you did is only based on meteorological data?
Yeah, in fact, it wasn't really clustering. I shouldn't have called it clustering. It was a really heavy-handed description. I think I used cloud cover and said less than 10% cloud cover is clear, 10 to 90 is partial, and 19 above is overcast.
And you didn't try the clustering based on the correlation?
Yeah, absolutely. That's what should be the next step, is to do this kind of semi-supervised thing where you design the clusters specifically to optimize the covariance structure. Yeah, I'd love to do that. So, yeah, if you have some ideas on how to do that, that would be great, because it's quite expensive testing it. So once if you want the function you would want to reduce would be very expensive to evaluate. If it was a variogram score, for example, and you wanted to evaluate it for these clusters, maybe thousands and thousands of times, it would be very, very slow. So, yeah, I think that would be a challenge, but one worth thinking. Okay, so now something familiar from this morning. So, in very short-term forecasting, we love vector autoregressive models. So, it should be familiar from this morning's talk. But we have the same issue. Of course, we have the same issue because it's the same problem. It's the number of parameters we have to estimate increases with the square of the number of wind farms we're interested in. So here, each YT vector is a vector of power output from one wind farm and some multiple wind farms from some point in time. And we think there's some spatio-temporal relationship between them. So understanding what happened not only at the same wind farm in the past, but wind farms in the same region in the past can help us improve our forecasts. At least that's the theory anyway. So the first thing to do is maybe think about some sparsity. So we had one approach using principal components this morning, but of course we can try other things like Lasso or some other information criteria parameters, like the parameters we want to keep. I'm not going to talk about this anymore, but this is one nice problem in high-dimensional forecasting that we can maybe talk about another time. But however we estimate our parameter matrix, if we do this in the kind of the simple way, we assume that it stays the same over time. And that's what I want to talk about now. So I propose that this matrix of parameters, this spatial dependency structure, is also dynamic in the same way that we had the dynamic temporal covariance in the previous example. Okay, this is what I just said. And there are some quite simple things we can do to help it evolve over time. So a kind of recursive update to the parameters, for example, will track slope changes in the dependency structure. But if the dependency structure is a result of what's happening in the weather, then I think we should just look at what's happening in the weather and go directly to it. If we track things using like recursive least squares or something, then we always have some lag. But the changes in weather might happen on the order of days, whereas the memory of our RLS algorithm might need to be months or longer to be stable. Okay. And helpfully, these large meteorological phenomena persist for a long time. And also we can start to assign properties of our forecast to different weather types. So we know empirically, for example, that we tend to get large errors in the winter when it's windy, when it's possible to get large errors, and in violent weather systems are difficult to predict, whereas more stable ones are easier to predict, and we see that in our energy forecast as well. So can we use that to make better forecasts? So the kind of meteorological community has been talking about weather regimes for a very long time and how they impact predictability and maybe the source of predictability in some cases. So David already mentioned things like the North Atlantic Oscillation on Monday. And so now the question is, can we do something similar that's specific to very short-term forecasting? Because that's what I'm interested in for the next 20 minutes. So we had a go at this. And so the game is turning this very high-dimensional data. So these large-scale weather systems are obviously large, and the data that describes them is also large. So we might be talking about several variables on a grid that might be 100 or 200 or 1,000 units square. So it's high-dimensional data, and we want to somehow group it into a small number of groups that are relevant to our problem. So I'm sure most people are familiar with all the lists on here, so that's fine. We can have a go at doing this. Okay. I've said all this already. So this is the model we've seen already, where we just have one parameter matrix for all time. And this is a model we're interested in, where we can switch it for different regimes. I've jumped ahead here and shown you that for GB we found just 3 regimes were sufficient to give us nice improvement in forecast. But then we have this challenge that the more regimes we have, the less data we have to estimate our parameters. So there's always this trade-off between splitting our data into distinct regimes, but then not having enough data to get a good parameter estimate. So I was really interested here. This is what I was thinking about when you were talking about cross-validation earlier. We have a similar issue. How many regimes are optimal, and what should they be? Okay, so in this example, our regimes would find using a self-organizing map, which is a kind of neural network which takes this high-dimensional space and tries to describe it in low dimensions. So it's quite nice. Beyond just clustering, it has this nice property that in the reduced dimension, there's still some kind of relationship between the regimes, so they're linked into, the space is reduced. It's not like random labels. I'll show you the visualization after hopefully help. Okay. So all the blue dots up here are all our grid points in numerical weather prediction variables, and these X's down here are reduced feature space. Here they're in a line, but in actual fact they could be arranged in any number of ways. So it could be a grid, and that structure is important. So it could just be a smaller grid, or it could be a hexagonal grid or a triangular grid. And these relationships between neighboring states, if you like, or regimes, are an important part of the learning process. So it's outlined here in these 3 steps. So one is the competition. So how well does our reduced space describe the full space? And then all our states are updated, somehow moved towards the better description. And then the whole network is adapted, and you do this many times until you have a better or a good reduced dimension description of your data. So this is what we did. We did this using reanalysis data, over GB. Say we, this was mainly work of colleagues at Reading, so apologies if I'm a bit fluffy on the details. But using wind speeds, sea level pressure, and geopotential height to characterize our weather regimes. These are important for wind, obviously. And we were interested in forecasting the output at these 23 weather stations. So forecasting wind speed here, not wind power, I should say. Okay, so the self-organizing map had 21 dimensions in this case in this 3x7 grid, and hopefully this kind of explains what I was talking about with the structure of the reduced dimension space. So the neighboring regimes here are related to each other. So if we go along the top row, I think is mainly low pressure systems, and then we've got high pressure systems on the bottom row and some kind of lower pressure gradients in the middle.
They are not supposed to form a basis as if you were doing PCA, right? They are more typical.
So yeah, I think it's kind of like a non-linear type of PCA. So I don't think, I don't know. That's
Okay.
the answer.
I don't know is the answer.
I'm not going to try and.
But you have an ordering and cross those dimensions in some feature at least.
Yeah.
This was the problem we had with Costas when he was doing this. Did you choose the geometry of that grid beforehand, or how was there a discussion of how, why? Why
Yeah.
is it 3 by 8 where it is?
Yeah, so
rather than another.
So using some kind of information criterion. So we wanted the simplest grid with the fewest number of nodes that described the greatest or the largest proportion of the information in the raw data as possible.
So you specify a number of trials and then find the one that works best. Or it's not.
Yeah.
It's not a sort of an output of the algorithm. It's something you put in at the start and try to inverse
Yeah,
from that.
yeah, exactly. So that's what Costas did.
Yeah.
Okay. So now the question is, these have been chosen based on this information criterion, but what's best for wind power forecasting? Do we just take these 21 modes and train 21 vector autoregressive models and switch between them for our forecasting, or can we do better? And because of this issue of reducing our training data, we split. In this case, it was 5 years of training data, 2 years of testing. If we split our 5 years of training data into 21 modes, all of a sudden we're training on very little data. So we get nasty, noisy parameter estimates. So we did some trials by further reducing the number of clusters, this time just using k-means. And for the wind power forecasting application, we found 3 was optimal. But we also, Dan and Costas had to go at just eyeballing the regimes and grouping them themselves to kind of come up with some kind of expert judgment on the number of regimes that would describe different spatial structures in wind power production, or wind speed, I guess. And they didn't do quite as well.
So how many points do you have on the map?
23.
Yeah. I guess they were not covering the same amount of situations one that you had previously.
Well, so any one real situation would be assigned to one.
Yes, so some of these clusters are smaller than others.
That's true. Yeah, that's true. I've got a histogram on in a couple of slides to show you when they occur. So these were the 3 we came up with, and maybe not unsurprisingly, one's a strong low pressure system, one's a strong high pressure system, and one's not very much going on situation.
Where were your 23 zones kept? Where were the 23 test points though?
There we go. So quite a lot in the Midlands, a few in Scotland, just one in Cornwall. Yeah. Okay. But I think when it comes to the spatial structure in our vector autoregressive model, it's interesting to look at the wind speeds in the 3 modes, right? So in one we have higher wind speeds in the south and low in the north. In one they're fairly uniform, and in the other we have high wind speeds in the north and low in the south. So there's kind of some stretch down already.
Do you think it could be interesting to couple detection information to physical forecast, for example. Grid forecast should. I mean, maybe it's a silly question, but to have a lot of points on the space. For doing a because you do a clustering with only 23.
I know the clustering is on the 21 modes. So the clustering, we have 21 regimes, and we're further grouping them. So we're clustering on these to produce, to group these in. I think I've got a nicer picture. So yeah, so here are the 21 modes in this 3x7 hexagonal grid. And then the colors indicate how they're further grouped in the clustering. So we have 3 regimes. So we haven't seen the station data yet in this process. And also, you see that regimes 1 and 2 kind of summer regimes, if you like, and regime 3, which is a low pressure regime, very much a kind of a winter regime. So I guess as you would expect.
What's a bit annoying when you do that is you do it independently of the actual process you care about,
Yeah.
and you're just hoping that there's going to be something, right?
Yeah, it's the same problem again.
Yeah.
I agree. This is something we could do a lot better. So here's some results. We see again some nice improvement. So the red line along the bottom is a very naive far with no daily seasonality. So there was a lot of daily seasonality in the status diurnal pattern, which is taken into account with the dark blue crosses. And then we wanted to understand if we were simply correcting a bias. So we just have a different bias in our model in these 3 regimes. So we tried to account for that by including just a simple dummy variable for the regimes, but that added no value. But when we had a completely separate parameter matrix for each regime, we got consistent improvement across forecasts from 1 to 6 hours ahead, is what we were interested in. Okay, so maybe just to...
Sorry, just again to understand, for every forecast day you're doing your forecasting, do you assign one regime directly, so 0, 1, 1, 1, or do you have a probability for being in a certain regime?
No, just deterministic.
Deterministic, so just
Very
100% in this regime. And
Yeah, we don't do any kind of mixing or anything. So quite simple.
just to
You have to stop. Actually, related to what I said before, why didn't you try the fully data-driven approach with the Markov switching, for instance? And you say, okay, I just assume there's 3 regimes, like here you end up with 3 regimes, and I'm just going to learn it by filtering through the data.
But then and filtering through the grid of NWP data.
No, directly. Because what you hope here is that it has an impact on the actual time series you care about, right?
Yeah.
So by filtering your time series, it's like the change point detection of yesterday. You detect different regimes, and in plus it has the advantage that if you do it in a Markov switching framework, then you have this transition probability matrix that also allows to iterate.
But you're always going to observe the regime with some lag, right? If the regime changes, you at best you're going to notice it one step after.
Yeah, but very short-term forecasting. You say so you have data every what every.
Well, yeah, exactly. Yeah.
So you.
No, I agree, but we wanted to do something where we weren't lagging in reality. We know we're in a new regime, so we choose a new model in advance.
But at least I think it's worth to compare. There's his name's Pierre Elliot and Valérie Mombé. They released a package for Markov switching VAR models.
Right.
computational equation, isn't it?
Well, you can also do online learning for this kind of thing.
Yeah.
But I mean, you
So
could
we
try to have an extra line at least.
Yeah,
to
we
see.
should compare. For sure. I think I just wanted to point out that the improvement was across all the 23 sites. Those average results aren't just because we saw a big improvement at one location and not everywhere else. It was kind of uniform across all 23. And also the kind of final point, this is deterministic forecasting, but we also have very different error distributions in each mode as well. So for the next step in going probabilistic, there's useful information here as well. Okay, and I think that's me. So there's some references. There's 3 problems I've been working on, and it'd be good to talk about. So yeah, any more questions? I'm happy to take them, or we can.
You had with Kieran, you had it was that you won the forecast competition where it was also region-based. But it was also for wind, or it was for prices?
It was for wind, and it was a badly designed competition. Because
okay, so it doesn't count.
the task was predicting day ahead, but without NWP.
Okay.
So we used an autoregressive model for forecasting day ahead, and
you just also.
And every forecast was just the game really was what's tomorrow's mean going to be. Right?
Yeah.
So
Okay, so it was not this kind of thing.
it was similar. You know, we did clustering. We said, well, based on today's mean, we'll have tomorrow's mean. But that was a funny competition.
For the conditional covariance structures. I mean, maybe same story, you know, with some kind of Markov switching approach. At least you could try to model how they may be transitioned from your different regions.
Yeah, for sure. And also when it's a parametric covariance matrix, right? The whole, even though it's a big matrix, might be defined by a single parameter, and that is that one parameter or a small number of parameters that should perhaps be a function of the region rather than.
So you could, for this matrices A that you finally want to adapt to the regime, you could model, let's say, an average matrix, and then additional deviations from the average, which you could try to regularize so that they are sparse and have some structure. Do you think of this kind of, does it make sense?
I don't see how it's how it would give you a different result. I mean, I see how if you somehow impose
Somehow
very
it's
sparse, then it could be
imposing
helpful.
the sparse differences between
Yeah.
these matrices.
Yeah. Yeah, I need to think about it. And when you go to even larger scales, you want the final matrix to be sparse as well, right? Because you're not going to have strong relationships between wind farms at opposite ends of the country, or demand nodes at opposite ends of the country, or even between a demand node and a wind node if there's no embedded wind, for example. So I think this sparsity issue, I mentioned it in passing related to the var parameters, but it applies equally to the covariance matrices. So maybe some kind of graphical model or similar that you can regularize would be really nice to use there.
So based on what you showed us, and as a transition anyway for what we have to discuss later, then what are the challenges today for which we need a bit more mathematical source?
So for me, it's turning all this detailed information into something useful, right? Even if you could model all the spatio-temporal structures on the 500 nodes of the transmission system you're interested in, it's not useful. So it's then how do we aggregate or otherwise extract the value from that information? I think for me is one big challenge. For all the nice estimation issues as well, we want to get our forecast as accurate as possible, structures modeled as well as we can. But
so that means the challenges are on the side of those who do optimization afterwards with it, or?
No, I don't know. But I think we also have a responsibility to give them useful inputs, right?
Yeah.
We spoke to a lot of optimization people in the first week, and there's a big disconnect between what we're doing. We just assume that if we produce loads of good scenarios, then the optimization people will solve it. But maybe what we should be thinking of, well, if we make a forecasting model that can very quickly reduce and produce a subset of scenarios that's more relevant, that would be really valuable. Or something similar.
And there's once at a conference, there's a guy, I was giving a talk on not the same topic, but also about trajectories. And it depressed me because at the end of the talk he said, you know, Pierre, you give me the lowest trajectory, the highest trajectory, the the deepest trajectory, and thank you.
Yeah. Well, that's it. Like in the optimization settings, the result is going to be dominated by a small number of events. You know, whether it's the timing of something or, you know, a lot of the variability doesn't affect the final result, but in some specific cases, maybe some parameters at some times, the result will be very sensitive to that. So I think we need a better way to deal with it.
Okay, but how does that translate into let's say an estimation problem, for instance? We need to somehow know what's the value of the product you provide in their machinery, and then you estimate the parameters in your machinery or the type of product you want to issue based on the value for your forecast.
So in the spatial case, let's say what you're really interested in is the flows between Scotland and England, for example. You might model all the dependencies and have this complicated forecast information. But what you really want is the net, you know, the aggregate on both sides of some boundary. And that boundary might change all the time. You know, all of a sudden it might be a different boundary on the transmission system, or it might be some other decision-making problem, but it's always going to reduce to quite a simple setup, similar to the kind of the
But you
bus
showed
model.
an example with the wind farm where you basically use this lower level kind of forecast. So I think this is something that you can reproduce at higher level as well.
So you want the detail because it's valuable, but at the end of the day, you might only be interested in a few aggregate quantities.
Yeah, but in a flexible way.
Yeah, but yeah, exactly that. Maintaining that flexibility is a challenge. You can't retrain a model to forecast all the aggregates on the fly.
What about the connection to demand response problems? Like if you can also have the same kind of model for smart meters in the same region, maybe it would be interesting to have a common estimation of production, consumption, derive the context of the net consumption.
Absolutely.
Locally. I think it's interesting because there is correlation between because of the weather.
Yeah, but exactly. But when you want to aggregate, you need the correlation structure. So.
So did you look at, simultaneously solar and wind?
Not so far, but it's on my agenda.
It's quite weak. I mean, the dependence. It depends a lot, I guess, where you are in the world. Also.
Yeah.
But the dependency is quite weak. It's
But
only
we're
like
talking
in Texas.
in forecast. We're talking about dependence in forecast errors, right? Not
Yeah, but even forecasters, I mean, it's not so. I don't think it's so strong. I mean, I think it's a relevant question, and if you want to be consistent, you go all in for all
Because
the
he
structures.
found that, I think the wind speed or whatever is somehow giving information about how well you can forecast, right? It's something that you found already for the solar. So I guess this is.
I think it maybe depends on the weather situation, right? So if you have some weather system which is bringing both cloud and a change in wind speed, but you get the locational timing wrong, then you'll have a strongly correlated response. But if it's different, if it's a different process driving the errors for different resources, then they'll be uncorrelated. So it's dynamic, and we should try and model.
One problem to me always seems to be going back the opposite way around. It's, you know, you can say, well, you know, give me a forecast of X. If you know what X is, that's fine, you can start to tackle that problem. But half the problem here is you don't know what things that we most care about, whether it's wind ramps or whether it's the wind in these Drift 3 sites, or whether we build a load more wind farms, or whether we mix it with a certain fraction of solar, how much solar. That it's a mobile target, so sort of. So it always seems to be there seems to be some sort of thinking around how you efficiently identify the targets that you most care about, beyond just brute force simulation, throw all the data through and get an answer. But that certainly answers the question now. It doesn't answer the question of how it might change over time. So that to me seems to be one of the central challenges, whether that's something that's formulatable as a mathematical probably well, not I don't know, but
I think we can design our mathematical models to be flexible enough that when they're asked a question, they can try
Yeah.
answer it.
I think it's the same. So if you once you have say a multivariate model which describes everything,
Yeah.
and we are able to draw the trajectories from it, and then we talk to practitioners and they tell us, well, but I'm just interested in the flow between England and Scotland. Then I draw more trajectories from this say interesting region and maybe a few from the other ones, and then give him the information, and then he can optimize based on his part.
Yeah.
But of course we need then the weights for the corresponding trajectories and so on. But basically I think this is the way to go.
Yeah.
And regarding the data issue, so the data you consider, they are open, or is it,
So the wind turbine level data, no, because it was given to us by the utility. But the solar data I showed was open. All the forecasts were from ECMWF. The wind speed measurements were are open for research from the British Atmospheric Data Centre. And in GB, you can get the wind farm metered power output from the Balancing Mechanism Reporting Service website.
For all wind farms.
Yeah, it's a recent thing. You know, a couple of years ago it wasn't there, but now it's appeared on the website, and you can write a little script to pull all the XMLs. So it comes
It's
from
embarrassing now that UK seem to be better at
but with
delivering
about
data.
with 2 weeks lag.
Still, first we don't care. We just love the data from the past, and
But it, you know, it is a bit messy in that you have to also pull the data for balancing actions, so you can identify. So it just tells you the meter, what was measured at the meter, right? So you also need to look if they were curtailed or whatever,
yeah,
which
but
is
the problem is
easily
always-
done. But you know, it's not it's a moderately large task to assemble a data set, but it is there.
They don't flag the data when there's been some action.
Well, you just have to get the other time series of actions. And then you
That's
compare.
all.
Have lots of fun.
So you mentioned that you have handled the wind farm separately. Actually. So if in the future we have more and more wind farms, it will be like a single big wind farm for the whole for big area. So I think maybe you can try to exploit simultaneously the data of different
I think so. Especially offshore where we have these clusters, and even if the clusters spread over quite a large area, they're all connecting at 1 or 2 nodes on the transmission system. So they don't care where the wind farms are, but the injection is coming at exactly the same place.
That's why for us in Denmark, they don't give us the data per wind farm. It's per injection
Yeah.
point where they're connected. Just pull the turbines
That
together.
will change. In the future, if we have lots in the North Sea, there will be possibility to have a network.
Ah, yeah,
Sea
yeah,
network.
sure.
So then the point of injection will not really be
Yeah.
static anymore.
Back to this data, you said it's anyone has access to it, or you need a UK affiliation? Or?
No, anyone with an internet connection can see it. So I don't see why you can't. I don't see it.
But didn't you say you needed a subscription yesterday? Or?
For
For the wind farm data, it's through the website of the electricity market.
So there are 2 routes. So there's one's the full set of all the settlement data, which includes a lot more than just wind farm production. You do need a subscription for. But if you go to the
To JethroBrowell.com.
I should put a link there. maybe.
Actually, yeah. So, okay, we're going to discuss that afterward, but if we wanted to tell people, look, if you want a high-dimensional data set for wind farm, it might be your best shot, because for Denmark, it's sure it's not possible. For France, it's sure it's not possible. In Germany, it's just not possible. In Italy, I don't think it's a good idea. The quality of data is varying so much. No, but there's lots, I think, there's lots of reasons why. If this was really available, I think that's a very good data set to share.
Okay, now we have to guess the wind farm name.
I have to finish. We have data from Sardinia.
be a new ID for Wiley.
For what?
Well, there should be a list on our IDs, isn't it?
Yeah, it's
This is where no one finds this thing.
yeah. Okay, if you know the ID.
Okay, they want to make it simple, right?
I don't know.
Okay, but are you randomly trying something? Because
No,
so it looks like
You can write a script.
it's very embarrassing.
yeah, exactly. Where you try all potential doing.
Then we
They should never do a live demonstration.
No, it's very cool, interesting.
I'm sure we have best things to be doing. Where's one else? Where's mine? There we go. It's got a W in it. It's here, I mean. You have to trust.
Okay, but I mean, we can discuss that after. Could be a good idea. Have you not extracted it already?
Oh, yeah, okay.
So without the T. There you go. So it's this is where it ends.
And at which frequency is that then?
Should be market resolution, just 30 minutes.
30 minutes. So this is the big wind farm just south of Glasgow. But you have to write a script to pull the XML on a daily basis, kind of thing.
Yeah, you have
So you have to leave it over the weekend, and you might get a couple of years worth of data. Anyway, is that?
As you can check the CSV as well.
That could be a way. But yeah, I would propose that we break now and